right?
Yes, I can hear you very well.
Okay, great. All right, so yeah, I'm going to be talking about Monte Carlo integration, and it is a method of integration that approximates a function's value rather than solving it analytically. And it is used a lot in statistics, finance, and physics, where solving integrals just become too complex because of its potentially multi-dimensions. And how this works is we choose n random points over the function of interest and evaluate the function at these points. And this method is largely based off of Poisson's law of large numbers, where we're performing an experiment a large amount of times. The average of those experiments should converge to the expected value within a range of error. And yeah, okay. So we are going to be talking about just this simple one-dimensional integral for ease of explanation. So we've got a function f of x, and we want to try solve this through a Monte Carlo method. So we have two methods of Monte Carlo integration, that being the uniform method and importance sampling. We'll get to a bit later. So the uniform method of Monte Carlo integration samples its points randomly from a uniform distribution, having no bias in its sample points. So if we could take point xi between the width a and b, we can multiply xi by the width to get the area of a rectangle. And pretty much the idea of this is that we could sum the areas of those n areas to average these to gain the approximated value of our function of interest. So so taking n points from our function, we get visualized points like this along our curve. And going on to our next slide, this would be, this is the formalized uniform Monte Carlo estimator, where you have our width and our number of function evaluations multiplied by the sum of our integral, and our margin of error being the standard deviation over the square root of the number of function evaluations. Okay, and so for our next method, we're going to be talking about the importance sampling method. And it's just another method of Monte Carlo integration, but instead of sampling points completely randomly from a uniform distribution, we pick a distribution that looks roughly similar to our function of interest. And doing this, we are able to sample more significant points along our function of interest. Significant points meaning points with a higher area under the curve. And yeah, so this is going to be our formalized importance sampling method with our margin of error just being our variance squared. So what's the difference between these two? The uniform method of Monte Carlo integration samples points randomly along the function of interest. Though this approximation is accurate, there is room for improvement. Importance sampling is a method of variance reduction sampling, sampling points from distributions that look roughly similar to our functions of interest. This gives points of our function that are more significant than others. And yeah, as I said before, more significant points are points that have a larger area under the curve. Think of a normal curve. Values one standard deviation away from the mean is much more significant than five standard deviations away from the mean. Okay, so we have made a practical example with this integral. And what we're trying to show is the differences and similarities between those two methods of Monte Carlo integration. So going on, oh, that's really bad quality, but going on from our first uniform method of integration, we've utilized packages from, I think, NumPy and Stats. And we were able to provide n being 10,000 function evaluations, and the area of interest being between 0 and 1.5 to the pi, as said before. And we find our integral value being 0.995, with the real value of the function being 1. And finding the calculation error mentioned previously, we get 0.02 thereabouts. And yeah, so we did the same thing for importance sampling. And yeah, so n being 10,000, min max being the same, but we did this over a normal curve, because we'll see why in a second. So we get the integral value 0.99 with error value 100 times less than previously. Yep, so this is our curve that we're interested in, between 0 and 1.5 pi sine x. And this is our normal curve that we've decided to sample points from. So you could see that they are roughly similar. A lot of the points are going to be sampled around this peak, which will correspond to important areas of our function, which are around this peak. So intuitively, you would think that it will derive a more accurate approximation from these more significant points. And just these two methods visualized against each other, the first one being from importance sampling, where a lot of the points, each blue point is a random point chosen. So you could see here that a lot of our points are sampled around significant parts of our function. And this is compared to our uniform sampling, where a lot of our points are sampled against points that are not too significant at all. And I think that is it. So thank you for listening, and any questions?
You are welcome. Thank you very much for the presentation. Good. Maybe other colleagues, they have any question?
I just wanted to say thank you for your presentation.
Beautiful. Just I was wondering to know, do you have any information